great to be here again. I was reminded this morning that the last time I was giving a talk in ISR was probably 11 years ago, so time flies, so it's really great to be back. So today I'm going to talk about something that's related to a very modern problem in communications, which is machine-to-machine communications. So I think probably everybody here knows that right now the development is ongoing for the fifth generation of mobile networks. And the first four generations, or I would say the first, not the first one, but the second through the fourth generation, were all driven by, I think, ideas from information theory, the development. So the first generation was analog voice. The second generation was digital voice and texting. The third generation was web browsing, on mobile web browsing, if you will, mobile data. And the fourth generation was basically video streaming, if you want to think about sort of the basic ideas that came in there, all driven by ideas from information theory. But one of the common things about these four generations is that they were all designed for this, right? For not a smartphone, but for some kind of end device where the end user was a human being, right? And so human beings, we perceive things in a certain way, and when it comes to latency or delay in communications, human beings are not sensitive to delays on the order of 100 milliseconds or 200 milliseconds. So when you're talking on the phone, obviously you're not talking in instantaneously real time to someone, but rather there's a delay through the network. But you don't notice it because the network is designed to have delay tolerances of something like 150 milliseconds, okay? But with the fifth generation of mobile networks comes the so-called Internet of Things, in which the end users are not telephones or not human beings, but devices, machines. And machines are less tolerant for delay, particularly machines like automobiles that are driving down the highway, things like that. So delays become much more critical. So 100 milliseconds is too long. And so one of the big things about 5G is to look at what they call low latency communications. The acronym you hear is ultra reliable low latency communications, which is designed to support the Internet of Things, okay? And the thing that I'm interested in here to talk about today in that context is that brings up a new regime of fundamentals, okay? So information theory, as I said, drove a lot of the development of generations 2 through 4, but information theory is an asymptotic theory, okay? And so it's not very applicable when you're talking about low latency communications. So let me take off on that theme. So that's what I'm going to talk about today. So this is really talk about theory for low latency communication. So let me start with a little bit of motivation. So I mentioned the Internet of Things. So the Internet of Things is a vision of a network in which the endpoints are, the end users are machines, and there are many, many applications such as autonomous driving, which we hear about a lot, but also in agriculture, robotic surgery, or telesurgery, things like that, and so forth. So there's a lot of applications where the endpoint are machines, okay? And when you're talking about human beings, there's 7 billion human beings. That kind of puts an upper bound on how many of these there are going to be. But there are many, many more machines. So one of the aspects of the Internet of Things is the massive connectivity that could be come about from that. Hundreds of billions of devices rather than under 10 billion devices. And of course, most of this is wireless. So I'm mainly interested in this because it's part of the 5G wireless area. And so that's where this comes about. So some of the salient characteristics of the Internet of Things, first of all, massive connectivity, as I said, high energy efficiency, so a lot of work and sustain themselves in terms of energy. They don't need to be recharged or have battery replacements. Low complexity, so a lot of the things are sensors that cost $10 rather than this kind of thing, which costs hundreds or maybe even $1,000. Very low complexity. They have to be highly reliable if you're thinking about something like automotive application where people's lives depend on reliability. You need highly reliable end devices. Two things that I'm going to really focus on here are short packets. So oftentimes the messages are very short. So we're not talking about video streaming here or playing or virtual reality or anything like that. We're talking about short commands or a measurement. So from a sensor sends a measurement, it doesn't take a lot of bits to send a measurement or to send a command. And then low latency, as I said before, latency becomes much more critical when you're talking about automation and things like that, where there are dynamical systems involved that have time constants that are much faster than the human ability to perceive delay. So just to give you an idea, this is from one of the 5G standards documents. And what I want to focus on here is the left column. The columns over the left, you can see so I mentioned that for human beings, we're talking about 100 milliseconds or something like that, or 150 milliseconds of imperceptible delay. But if you look at these applications here, these are automotive applications, smart grid, things like that. We're talking about delays. The largest one there is 50 milliseconds, but some of them are down to a millisecond or 5 milliseconds, even half a millisecond for some kind of applications. So we're talking about latencies that are very, very low compared to what current network can support. Okay. So what I'm going to talk about now is not so much the practical aspects of this, but what are the underlying fundamentals of this, okay? And information theory traditionally is an asymptotic theory as the block length goes to infinity, so you basically want to know what happens if I can code over an infinite amount of time. What's the fundamental limit? What are the fundamental limits? That's what Shannon developed. It's a beautiful theory and it drives a lot of practical stuff, but if you're thinking about short packets, you need to think about information theory, the non-asymptotic information theory, that is finite-block-length information theory. So what I'm going to do, I'll say a little bit about traditional information theory for those of you who may not be in that field. Then I'm going to talk about some of the basics of point-to-point finite-block-length information theory, which is much more recent development. Then I'll talk about some multi-point models, that is network models. I'll talk briefly about age of information. I feel a little bit apprehensive about that because Shannon is one of the experts there. We have others, of course, at Maryland who are, at Maryland who are experts in this field, and I'm just going to talk very briefly about this, and then I'll wrap up. Okay, so first of all, traditional information theory. So what is that? Well, pioneered in the 1940s, so we're talking about 70 years ago now. And Shannon looked mainly at point-to-point channels at two problems. One is data transmission, which gives rise to error control coding. And the other is data compression, which gives rise to source coding. And I'll say a bit more about that in a second. And then, of course, over the years, there's been a lot of developments in so-called network information theory, looking at these problems for other channels other than point-to-point channels, so broadcast, multiple access, relay channels. And there's also interest in secure transmission, the Wiretap channel, which has taken there's been a lot of very recent interest in that area, and also secure compression, another area where there's been a lot of recent interest because of many of the same applications that I talked about earlier. This is an asymptotic theory, that is, Shannon theory is a theory that characterizes fundamental limits when delay is unimportant. And of course, as I said earlier, it really characterizes things in a very simple, elegant way that drives real operational engineering insights. Okay, so a lot of things that happened over the last 35 years to develop the first 4 generations of mobile networks, really driven by insights from information theory. Problem is, it's not suitable for low latency applications because it's an asymptotic theory. Okay, so what is this asymptotic theory? Well, a very basic model for communications is the one shown here. You've got a source. It takes one of m possible values, so the number of bits in the source is log 2 of m. A source symbol W is encoded into n channel uses. X to the n is a sequence of n channel symbols. They're put into the channel. The output of the channel comes corrupted symbols, n of them. Those go into the decoder, and the decoder tries to recreate the source with as good a fidelity as possible. And very fundamental idea of Shannon's is that every channel like this has a capacity, which is the largest rate, that is the biggest m basically, that you can send in relative to the number of channel uses as the block length n goes to infinity and the probability of symbol error goes to 0. And that result, that number is the capacity of the channel, and it's the maximum over the input distribution of the mutual information, I, between the input and output of the channel. Okay, so it's a very simple, elegant result. And knowing this gives you a target to look at if you're designing practical codes and so forth for a given communication channel. For data compression, so that's for data transmission. For data compression, we have a different problem. We have a source X, an encoder. We'd like to compress it down as much as we can into as few bits as possible, either for storage or transmission. At some other point, we want to decode it, and we'd like to recreate the source at the output of the decoder. There's 2 types of compression. There's lossless compression, where we try to recreate the source perfectly. And there we know that the smallest asymptotic rate for lossless compression is the so-called entropy of the source, which is just given a very simple formula in terms of the probability distribution of the source. And if we're not interested, so in transmitting media, we usually don't care about perfect lossless compression, but we care about so-called lossy compression. We'd like to, for a given level of distortion, we'd like to find the smallest rate that we need to store or transmit the source, and that's given by the so-called rate distortion function, which just tells us the smallest rate that we need for transmission of the source at a given distortion level. This is all very classical stuff. I'm just putting it out there to inform what I'm going to talk about in a minute. Okay, so that's all asymptotic. Okay, this is all asymptotic theory: data transmission, block length goes to infinity, data compression, asymptotic in the number and the length of the source. So now, what about finite block length? So what if we have finite block length? So first of all, what's important in trying to characterize these problems of compression and transmission? Well, for transmission, the important thing to study is the so-called information density, which is the log of the the joint probability distribution between the channel input and channel output, divided by the product of the marginal distributions of the channel input and channel output. This quantity, the expected value of this quantity, is the mutual information. So this is what we maximize in the mean to get the capacity. And in the case of lossless compression, it's the so-called information density that we look. The information that we look at, which is just 1 over which is the log of the probability distribution, or the so-called detilted information, so the expected value of the information gives us the entropy. The expected value of another random variable, the detilted information, gives us the rate distortion function. So they're similar quantities that play similar roles in compression as the information density does in transmission. Now, just to give you an idea of the importance of the information density, even for finite m and n, so finite block length and finite error, the the smallest error for a given code of length n and m code words, that is log 2 m bits in the source, can be upper and lower bounded here in terms of the information, the probability distribution of the information density. So here you see it appearing right here, okay? And both upper and lower bounds are determined by the information, this probability distribution of the information density to within some tolerance which goes to 0 as n goes to infinity. So this just illustrates that the information density is sort of a key thing that determines the ability of the channel to support traffic, to support rate, and it's true even in the finite word length or finite block length case. For every n, it's important, not just asymptotically. Okay, so it turns out that in both the case of transmission and compression, the non-asymptotic fundamental limits are also characterized by these quantities, okay, which I just said. And we can't get exact expressions like we can in the asymptotic case. For example, the capacity we know is the expected value of the information density maximized over the input distribution. But we can get very good upper and lower bounds. So upper bounds in this case are called converses, and lower bounds are called achievability bounds. And that allows us to see what are the higher order terms in the capacity, if you will, for finite block length. What is it that's disappearing as n goes to infinity? So those are important terms when you start looking at finite block length, okay? And these upper and lower bounds allow us to refine the asymptotic limits and look at how actually the capacity, for example, is converging to the Shannon capacity. Okay. So here's an example. This is for, again, the point-to-point data transmission problem. So again, we have a source. We want to encode it in n channel uses and reconstruct it at the decoder. And for finite n and epsilon, so epsilon being the symbol error probability, we're interested in what's called an n-m epsilon code, which is a code that allows us for a given source size m and block length n, allows us to reconstruct the source at the output of the decoder with a probability of symbol error no more than epsilon, okay? And a fundamental limit is the largest m for, if you fix the block length and the fidelity, epsilon, a fundamental limit is the largest m, that is the largest number of bits that we can transmit within those tolerances, okay? So this largest m for which we can find an m epsilon code, okay? And if we were to divide that by, take the log of that, m star, and divide by n, the block length, and let it go to infinity, we get the capacity. That's what Shannon found. But it turns out that if we look at the finite block length case, we can get a pretty good approximation to that for finite n. And in fact, it's given here. This thing goes to the capacity as n goes to infinity, and there is a capacity right there. But it's for smaller n, there's another term, which is a 1 over root n term, and it's determined by two things. It's determined by epsilon, the fidelity, upper bound, and q here is just the tail of the unit normal distribution, and q inverse is the inverse of that distribution. And v is the variance of the information density evaluated at the Shannon capacity achieving distribution. So the capacity is the expected value of the information density, and the next term, which is called the channel dispersion, is the variance. So as you might expect, the second moment of that information density now comes into play to give us the next term in the asymptotic expression of the capacity. Now this is an approximation, but it's actually equal with a higher order of log n, okay, in general. This is for memoryless channels. And you can refine the order log n for specific channels. Sometimes it can be higher order than that, okay? But this is a pretty good approximation. If you look at the additive white Gaussian noise channel, for example, this is with epsilon 10 to the minus third, and the signal noise ratio is 0 dB, under which conditions the capacity is 1/2. So this shows versus block length the an upper bound converse on the finite block length capacity and a lower bound, an achievability bound in blue on the same quantity, and also an approximation, which is the one I gave you there before. And you can see two things here. If you look at short block lengths, down here, 200, say, there's a big gap. The capacity is somewhere in here. Okay, we don't know exactly where, but it's somewhere in there. And say at 200, there's a big gap between the real capacity and the asymptote. Okay, and in fact, you can see even out there for block length of 2,000, there's still a gap. So it goes very slowly to the asymptote. So you know, there are a lot of codes now are 200, 2,000, or thousands, maybe even 10,000 symbols long. But if you're down here doing short packet communication and worried about latency, you have to be down here, and you have to worry about the fact that you don't have as much capacity as you thought. Okay. It also tells you when you look for codes, you can't be looking for codes at block length 200 that achieve the capacity, because it's not going to happen. It can't. Okay. The best you can do is what you see here on this between the red and the blue line.
But what other models is this computer?
Pardon?
But what other models is this computer?
What other model? Well, I'm going to show you one.
Other than the AWT.
Well, here's the binary symmetric channel. Okay. For the binary symmetric channel, you get a very similar picture. These parameters are chosen again to give a capacity of 1/2. And here, the approximations are not so good, but again, you have converse and achievability. So somewhere in that, between the blue and the red line, is the real capacity. That approximation is not so good here. This is because it's a discrete channel, I guess. You can add a half log into that and get a pretty good approximation. That's the black line. But again, the point is not so much the approximation. The point is that you see there's a big gap. In fact, a bigger gap here than an additive white Gaussian noise channel. And there are also some channels with memory and so forth for which this has been examined. So not every channel has been examined, but the actual result is pretty universal for memoryless channels. But the dispersion is a computable quantity, and you can look at dispersion very
If
soon.
you look at real wireless samples like you look at in IoT, any computation in that regard?
Yeah, so there are some, well, when you start adding fading, you get some other situations, right? And so there are some computations like that, and also some channels with memory. You pretty much always see the same kind of thing.
That's already worse than this?
I wouldn't say worse, no. They're similar. I mean, partly because the capacity changes too, so it's all relative to the actual asymptote.
Thank you.
Yeah. Here's an example of something you can do with this, of a more practical nature that you can do with these approximations. So this is, so an important thing in the Internet of Things is the trade-off between energy efficiency and spectral efficiency. Because when you're talking about terminals that are self-powered or powered by energy harvesting, energy efficiency gets to be a much bigger deal. And you can see here, if we look at the Shannon limit, we see a certain trade-off between spectral efficiency and energy efficiency. But I think this is a very short block length case here, something like under 20, block length of under 20. We start seeing, if we require higher and higher fidelity, we see we need a lot more energy for a given amount of spectral efficiency to achieve the same trade-off, right? And in fact, even though this kind of chart didn't have anything to do with it, I don't think, if in the standard, the 5G standards, they're talking about energy efficiency, spectral efficiency trade-offs that are sort of half the Shannon limit for IoT. So they know, I mean, people know from experiment that this is the kind of thing you get, and this sort of verifies that from a theoretical point of view. We can also look at compression. So if we look at lossy compression, where we're interested in the rate distortion function, of course the asymptotic thing is rate versus distortion. But if we have a finite block length n, okay, then there are going to be times when we can't really achieve the distortion level d. And if we introduce a probability that that happens, epsilon, then we have a rate distortion function that depends on the block length, the putative distortion, and the probability of not achieving that distortion, which is equal to the rate distortion function plus another quantity, the so-called rate dispersion function, which is the variance of this d-tilted information. Okay, and then everything else is the same. There's 1 over root n, and there's q inverse of epsilon there. So same thing happens for lossy compression. And here's an example. This is a membrulous Gaussian source. Distortion set at 1/4, so this is just 1 point on the rate distortion curve. And epsilon is 10 to the minus 4th. The rates, these numbers are chosen, the d is chosen so that the rate distortion value of that d is 1. So this horizontal axis is the actual rate distortion value. And then here's achievability now as an upper bound, converse as a lower bound, Gaussian approximation. You can see again, for short block lengths, there's a gap between rate distortion and the actual minimum rate. Okay. For lossless compression, we have something similar. Now we have the best achievable non-asymptotic rate for block length n, and we have a probability of encoding failure, that is failure where we're not going to be able to reconstruct the source. And there, again, it's like a broken record. It's the entropy, which is the asymptotic quantity, plus another term. This is called the barentropy, which is the variance of the so-called information. And again, we've got 1 over root n q inverse of epsilon. So very familiar looking. And here's an example. This is a lossless compression of a Bernoulli source, allowing it not to compress, not to be lossless 10% of the time. That's just chosen so that 1/2 is the entropy of this source. And you can see this is a little more ragged. This is R star, and there's a normal approximation to it. And again, you can see a gap to the asymptotic limit. And it doesn't disappear very quickly. Oh, this is a very short, these are very short block lengths, but none of these things disappear very quickly. Okay, so the message so far is that for point-to-point problems, transmission and compression, what happens is we can find good approximations to the second order term. We can find the second order term, which gives us a good approximation to what's happening for finite block length. Okay. And that's based primarily on doing upper and lower bounds on things where we can squeeze the approximation before. Okay. Now what about networks? So, you know, when we look at wireless networks from a theoretical point of view, we often look at these small networks. So it's like organic chemistry, where to understand molecules, we try to understand bonds. So in wireless networks, at least from an information theoretic point of view, to understand the network, we try to understand these smaller networks. And one of the fundamental ones is the multiple access channel, where you have multiple transmitters and a single receiver. So in the sort of parlance of mobile communications, this is the uplink. Okay. And of course, the capacity is a region here because you have two transmitters, so you have to look at the rate of each of them. And it's well known that the capacity, at least for a membrulous channel, of the multiple access channel, in terms of the rate of user 1, the rate of user 2, and the sum rate of users 1 and 2, is upper bounded by some terms involving the mutual information of the inputs to the channel and the channel output, okay? And it looks like this. There's sort of a rate user, there's a maximum for rate 2, a maximum for rate 1, which are point-to-point rates. That's these rates, basically. And then the sum rate is also bounded, and that gives you this sort of, cuts off a corner. Okay, so that's what it looks like. Now what if we have finite block lengths? This is an asymptotic theory. As the block length goes to infinity, probability of decoding error goes to 0. Well, it turns out that it's much more complicated than the point-to-point case, as you might imagine. For example, for the Gaussian multiple access channel, where the channels adds added white Gaussian noise to the inputs, adds the inputs and then adds added white Gaussian noise to that, we can get achievability result. This only gives us an inner bound on the capacity region, which is given here. So just say a bit about this. So if you ignore these terms over here, okay, then what we have is the capacity region of the Gaussian MAC, okay? In other words, all this stuff is just describing the capacity region of the Gaussian MAC. So that thing I just showed you, in a particular case, is the Gaussian multiple access channel. But for finite block length, we have to correct that, okay? The correction terms, again, you see 1 over root n, right? Some other things that are variances where these are means. This is a mean. These v's are variances. So these are, again, channel characteristics beyond the capacity. And then it's basically to trace out the boundary of this achievability result. We just look at all these positive lambda 1, lambda 2, and lambda 3 that add up to 1. So you see they appear here inside this, these Q inverses, okay? So this gives us an inner bound on the capacity region. So M1 and M2 are the size of the alphabets that user 1 and user 2 can transmit, okay? So asymptotically, divide by n, let n go to infinity, these become the 2 rates, okay? So this is the finite length inner bound on the capacity region. And here's for the this is for the Gaussian MAC, and this is for, here's an example for a length 500, a block length 500, where both transmitters have equal powers, 0 dB. The asymptotic capacity, the one I just showed you earlier, is this red line, the outer bound with the dots, with the circles. The achievability result is this blue line in here, okay? And we don't know we don't know if this is the actual capacity, but we know that the capacity region lies outside the blue line. And we also can say that the capacity region lies inside some other places, like if we just draw the point-to-point capacities on here, finite block length, these are these red lines. So that we know that the capacity region is somewhere, the outer bound of the capacity region is somewhere in here. And in fact, we can look at, there's another upper bound that we can get by looking at cooperation between the 2 transmitters, and that's this dashed line. So actually the outer boundary of the multiple access region, the MAC capacity region, is somewhere between the blue line and the dotted black line. So it's very close. This achievability result is very close, at least in this test. And we can see that there's a big gap between that and the actual asymptotic capacity region. So same kind of thing. Sorry. Probably my best friend who wants to negotiate my student loan. Okay. Now so that's the Gaussian MAC. Now another place where we can get results is for the so-called MAC with degraded message sets, where one of the encoders knows both messages and the other encoder only knows its own message. Okay, so this is asymmetric MAC. There's no result that I know of for the most general multiple access channel. Okay, here. And here we get a result where the Again, the size of the alphabet for the source, 1 over n times the log of that, which is the rate, is equal to the rate, the asymptotic rate, with a correction term. And the correction term here, of course, is a plus, which makes you worry. You get higher rate for finite block length, but don't worry, you can't. The correction term is usually negative, okay? It can be positive for one rate, but it's going to be more negative for the other rate. And the correction term is sort of called the second order coding rate in this area. And it's given by a result here, which is not very illuminating, much more complicated than in the point-to-point case. But again, there's a matrix of dispersions that come into play, just like before. And here's just an example. This is with, I forget what exactly this is. But this is just an example. I can't remember exactly all the details of this example, but this is an example of that dispersion region, and you can see that one of these dispersions is always negative, and the other is mostly negative, and but it gets positive when the other one gets quite negative. Okay, so this just gives you an idea of the kind of region that this can be. Okay. What about the downlink? So the downlink is the model for the downlink of a cellular network is the broadcast channel, where you have a single encoder and multiple decoders. In this case, you also have a common message, W0, and then two private messages, or two individual messages for the two decoders. And again, we look for the largest rate region asymptotically. As the block length goes to infinity, the error probability on all of these different messages goes to 0. And now in this case, even for the asymptotic case, the capacity is not known universally. It's only known for some special cases. And the non-asymptotic, as you might expect, the non-asymptotic result is even sparser. So a lot of the things that are done in the asymptotic case, Martin's inner bound is the best known inner bound for this case, achievability bound. You can get non-asymptotic results of those kind of results, but there's not really any sort of silver bullet kind of results for this case. So there's a lot of open work here to be done for somebody who's interested in this. Another more satisfactory result comes from the wiretap channel. So the wiretap channel is a basic model for so-called physical layer security, where you're interested in the ability of the channel, the physical channel, to support secure communication, secure data transmission. This is the model that comes from Weiner. So you have Alice, who has a message, who'd like to transmit it to Bob reliably while keeping it secret from an eavesdropper, Eve. Okay? And here we have, in addition to the fidelity at Bob, epsilon, we also have leakage at E. And we'd like for epsilon to go to 0, delta to also go to 0. So epsilon is just probability of error here. And as the block length goes to infinity, we'd like to know that we could find a positive rate at which we can transmit in perfect secrecy to Bob, in perfect reliability to Bob, keeping it perfectly secret from E. And the maximum rate at which we can do that is called the secrecy capacity. And it turns out to be under some conditions, and I'm simplifying this a little bit, but basically it's the maximum over the input distribution to the channel of the difference between the mutual information between Alice and Bob and the mutual information between Alice and Eve. Okay, so that's a very fundamental result on secret data transmission. Now for the, again, not suitable here because if we have short packets, we can't really rely on this result. So what happens when we have short packets? Well, now we have to worry about finite block length n, finite fidelity epsilon, and finite leakage delta. And we'd like to look at the maximum rate at which we can transmit within those limits. Okay. Now, we don't have here a general result like we had for the point-to-point case, but we have, for certain special cases, we have results. So here, for example, is a semi-deterministic wiretap channel, where the channel to Bob is deterministic, meaning if there's no noise, and the channel to Eve is a binary symmetric channel. The crossover probability I don't see here. But in any case, there we can write R star in terms of the secrecy capacity, again, the dispersion and N appear there, and Q inverse now depends on delta, the Eve's upper bound, and epsilon, the fidelity of at Bob in the way shown there. So here's an example of this case, and here again we have achievability and converse and a second order approximation, and we can see again for finite block length, the secrecy capacity is much lower than the actual secrecy capacity. So the same kind of picture. Okay. All right, so let me talk about another aspect of latency, which comes into the Internet of Things, which has to do with the massive connectivity. Okay, so there's been a lot of interest lately in the so-called mini-access channel or massive multiple access channel, and so in the classical multiple access channel, you have a fixed number of users, and you look at what happens as the block length gets larger. Okay, that's the way you analyze the classical MAC, and we know as block length goes to infinity, we know the capacity region. Okay. Now, if you have a massive number of users or a large number of users, you might not be able to think about fixing the number of users as the block length goes to infinity, but rather think about the number of users growing with the block length. Okay, so if K is the number of users, then K of N is the number of users as a function of block length. And if we look at that as N gets larger, we can see something about the effects of massive connectivity on latency and other functions. So this is the so-called massive MAC, or the mini-access channel. So here we can look at the latency. Think about the latency per user as the number of channel uses divided by the number of users. And we can ask the question, at what rates of growth of the number of users with the block length is it still possible to get positive rate through this channel? Okay. Now clearly, if this is a constant, K is a constant, we can get positive rate. That's the classical problem. But what about other? That's not massive, right? That's just traditional. So what about other growth rates? Well, first of all, there's several results here. I'll just mention very briefly. So if the number of users grows linearly with the block length, then the same overall system rate is possible. That is, the sum capacity of the channel doesn't change when the number of users is linear in the block length. Okay. And if the number of users is polynomial in the block length, so here P is greater than 1, you can still get positive secrecy rate. Positive sum rate, that is system rate is called here. Okay. So you can even let the number of users grow polynomially with the block length and still get positive rate. Now here we're talking about asymptotics. Okay, so this is something where there's still work needs to be done on the finite block length case, but just says something about the massive part of it. On the other hand, if you let the number of users grow exponentially with block length, then the system rate goes to 0. That is, the sum rate is not going to support that many users with any positive rate at all. So the message is you pay a rate penalty for low latency, basically. Because if you want to have this to be small, by putting massive numbers of users in there, you're going to pay a rate penalty, and at some point you're not going to be able to communicate at all. Okay, so again, this is all asymptotic, so it sort of goes outside of what I was talking about before, but I think there are some interesting problems here to look at for finite block. I want to wrap up by talking briefly about age of information, which I mentioned at the beginning. So another way to think about latency is in terms of age of information. So the age of a piece of information, as the name implies, is the amount of time. So you think this is from the point of view of the destination of the information, right? So it's sort of the amount of time since the latest piece of information was received at the destination. So this is a quantity that's of interest in sensor networks. So you have a sensor that's measuring something, and it's transmitting measurements through the channel to the monitor, and there's latency in that transmission for whatever reason. And the monitor is interested in knowing how old is the latest measurement. So this is particularly useful in sensing systems because oftentimes you're sensing some quantity that's changing with time, and you're interested in what's happening now, not what happened yesterday. So think about measuring the temperature. You don't care what the temperature was yesterday, you care what the temperature is today, right? So it brings, in addition to distortion, which is the usual measure of quality of communications, it brings in another factor, which is age of information. So a piece of information is, you want to be able to recreate it well, but you also want to be able to recreate it quickly, right? So this is what age of information is about. Okay. So analyzing age of information is not really just an information theoretic problem. There are other issues, queuing theory and so forth like that. So why might you care about this? Well, I mean, why don't you say, well, a sensor takes a measurement, it sends it through the channel, and there you go. Okay. Why would you worry about age of information? Well, mainly it's back to this issue of energy efficiency. So in a sensor network, the sensors may not be battery powered. They may be powered by the environment, right? By either solar or radio, harvesting radio energy, what have you. So they may not always have enough energy to transmit immediately. So they take a measurement, and the sensor has to decide when is it going to transmit the measurement over to the monitor. So that's an optimization problem that can be examined using a combination of information theory and queuing theory and so forth. And you can get results like the following. For example, you can see that the threshold policy is optimal in certain cases where you send a certain update only if the age of information goes above a certain threshold, for example, things like that. This is work, by the way, that's done by Ahmed Arafa, who was a former PhD student of Shannon. Shannon has worked on this as well. So this is just a very brief example of another way of looking at latency and the kind of model you can use, the kind of results you can get. All right, so I'm going to wrap up now, and I have a little time for questions. So first of all, the first message here is that in next generation communications, latency tolerances will be much lower than in current generations. And mainly that's because of machine-to-machine type applications. Finite-block-length information theory is a way to think about latency in IoT applications, where the physical layer might be predominant. So, of course, latency depends on a lot of things. It depends on the network and so forth, right? But a lot of communications will be peer-to-peer, right? So the physical layer is going to dominate, not the network, okay? So that's where these kind of results can come into play. So what we looked at was point-to-point channels where the results are very clean. Multi-user channels where the results are not so clean. Secrecy, where for certain channels the rates are very clean. And I mentioned these large-scale networks. And I also mentioned age of information. All these problems, all these areas are areas where there's really a lot of work left to do. It's not really settled science here at all. So for graduate students who are interested in this kind of thing, there's a lot to do. And for other people who are interested. So that's all. Thank you.